Start now. Good morning, my name is Logan Shannahan, and today I'm going to tell you about a piece of experimental equipment known as the Polsky bar. First, I'm going to start off with a brief description of the stress and strain that Polsky bar is trying to find and the background about why you might build one. Then I'll move on to the actual physical construction of the Polsky bar, and finally going a little bit into the math behind how a Polsky bar works. Now, the only scientific knowledge I presumably have for the audience in this lecture is a cursory understanding of stress and strain. Everything else I'll cover. First, let's talk about dynamic conditions versus quasi-static conditions. Quasi-static is what most people think of when they think of stress and strain. That's when you have just any load sitting on whatever you have carrying the load, be it a column in a building or a brick or anything like that. And that's the time scale that we normally think of in human terms, seconds, minutes, however long. However, in certain applications, such as military armor or spacecraft or even collisions in cars, the actual stress and strain events happen on time scales much shorter, sometimes in the order of microseconds. This is what we term dynamic conditions. And it turns out a lot of materials behave differently under dynamic conditions than they do under quasi-static. Many are actually stronger. As you can see, this strength, known as rate dependency, is very interesting to military planners and other people working in these time scales. Now, to find out this change in strength, you can't just put it in your standard MPS machine, which is a large hydraulic piston used to find quasi-static strengths. They simply don't operate fast enough. So what you need to do is generate a controllable impact, as well as a way of measuring the stress and strain during this impact. And that's where a Polsky bar comes in. Now, the construction of a Polsky bar is actually relatively simple in theory. You have some method of generating the impact. That would be usually a gas gun of some sort. And this will fire a small iron bar of a diameter of interest. For example, a common diameter is a 1/2-inch steel bar, but you might also use 3/8 inch or some other diameter depending on your specific application. This bar, known as the projectile, is relatively short, somewhere between 50 and 150 millimeters, again, depending on your application. You can actually change this and get different length stress pulses, which is something I'll get into later. Now, what this bar impacts is another long steel bar. And these bars are made of very hard steel, known usually as American steel. Though you can use other materials if you want, but if you want to test very hard materials, such as, again, armor ceramics that the military might be interested in, you want to make a material for your bars that can hold up to the stresses involved. Finally, you put your sample somewhere in here, and then you add another bar. These bars are generally supported carefully with towers along the length so they don't bend, because it's very important that these bars be straight and properly aligned. Now, on these bars, to actually measure your stresses and strains, you'll have strain gauges. And being engineers, I would think most of us are familiar with a strain gauge. It does exactly what it says. It measures strain by giving you a voltage that changes with changing strain. So that's the basic physical construction. Now, how do you actually get a dynamic stress-strain curve out of this? Well, I'm going to explain that using what's known as an XT diagram. An XT diagram is simply a diagram of the position on the x-axis and time on the y-axis. And what you use it for is to track the wave propagation in the bar at the moment of impact. So, as the projectile strikes the end of the incident, or the first bar before the sample, two waves are generated. One travels down the incident bar. Another one travels back from the point of impact along the projectile. When it hits the end of the projectile, it reflects and then travels back to the end and into the incident bar. When it hits the sample, it will travel into the sample and reflect inside the sample. Likewise, once it hits the end of the sample, it will travel through and into the transmitted bar. Now, yes?
1 minute left.
I'm just about finished. Now, the lengths of these are very important to how we collect the data. As I mentioned, mentioned, the length of this bar can change. And in fact, the length of your pulse will be twice the length of this bar. So you have the pulse generated when you first hit it, and then the pulse generated after, or the end of the pulse generated when the wave has traveled and reflected from the end of this bar and back. So if this is 150 millimeters, the length of your pulse will be 300 millimeters. Now, how we turn this information into stress and strain in the sample is to simply record the strain at this strain gauge and the strain at this strain gauge. This is known as the incident pulse, this is known as the transmitted pulse, and there will also be a pulse reflected from the sample because of differences in impedance, wave propagation impedance between the material. Now, if we record all these pulses, we have strains at various times. Since we know these lengths and the wave speed in the material, as well as the strain, you can shift these pulses to the sample, convert for the difference in diameters, and then use Hooke's law to get stress. And what you end up with is stress, strain, and time in the sample instead of the bar. And now you can use that information to also get strain rate. If you do this test at a bunch of different strain rates, such as 1,000 per second or 3,000 per second, which are common strain rates that you can get on the Polsky bar, suddenly you know the rate dependence on the sample in that area. And you can say, for example, that my silicon carbide armor ceramic is completely 300 megapascals stronger at a strain rate of 1,000 per second than it is under quasi-static conditions. And that's very useful if you're designing armor. You can also use high-speed cameras to track more qualitative data such as fracture, but that's a bit more advanced. Thank you for your time.